Bye.
Thanks.
You're on. Crack on.
Okay.
You just mute it next time.
Okay, sure. Okay, so now we are going to discuss about the second part of the probability distribution, which is the normal distribution for the continuous case. So I bet some of us may have seen the normal distribution graph before. So it's something like this. It may also have a nickname called the bell curve. So it's like a bell. Right. And what we know that it is, first of all, one of the features of the bell curve or the normal distribution graph is that it is symmetric. It is symmetric about this middle line, right? And this middle line, in this case, it is 0, but in a generalized case, it's just the mean value, and then it's spread out evenly on both sides. Yeah. So actually, this is called a standardized normal distribution. We'll talk about that later. So what's a graph of a standardized normal distribution looks like? What about like other generalized cases or other different cases which is not standardized distribution? So we can look at the first example. So the first example is not something we are going to have during exams, or it's actually a exam paper or exam question, but normally we do not have this kind of questions. Normally we have for normal distributions all about calculations. I think this question is kind of like give us an idea of what's normal distribution, what's the graph of the normal distribution look like. So there are 3 different normal distributions, and we still have the same theta here. It reads follows. So x follows n 3049, y follows n 3016, and z follow n 5016. So what are all these values mean? Like what's the meanings of these parameters? We know that if I have a normal distribution, the first value is the mean of the distribution, and the second value is the variance of the distribution. So the first value measures the location of the distribution or the graph, and the second value measures the spread of the graph. So we know that for x and y, they both have a mean at 30. So it's like the line of symmetry for both x and y at 30, right? But because x has a bigger variance than y, so we see that x spread out more evenly than y, and y spread out like y is more localized compared with x. But do we know that y has a higher peak than x? Like y is like, because we know that they have, we can also draw something like x and something like y, right? Like x is also more spread out than y, and they have the same mean. But this is not the case, because we know that with the area of under the graph for each distribution, it is equal to 1, because just the sum of the probabilities for each value the random variable can take. So we need to ensure that the area under the graph for both x and y to be the same. So in order for x to have a larger spread than y must have a higher peak than x. This is kind of to ensure that, this is based on the fact that they have the same area under the graph. And what about z? We see that z follows a normal distribution 50 and 16. And 50 is the mean for z. So it is on the right-hand side of that. And it has the same variance as y. So z should have the same spread as y. Yeah, it's just like a translation of y by 20 units in the positive x direction. Right. Okay, so this gives us an idea of what a graph of normal distribution look like. And we know that no matter where it is, or no matter how spread it is, it still looks similar, or it still looks like a bell curve. And in fact, for each individual normal distribution, its graph is actually a translation combined with an expansion or contraction of the standardized normal distribution graph, right? So, for example, this one has a mean 0. What about I have a mean of 2, but with the same variance? We just like move this graph to the right by 2 units. What about I have a normal distribution with 0 mean but has a larger spread or has a larger variance? We just draw something like this, right? We just draw something like this. So we know that actually every normal distribution graph is a transformation from the standardized normal distribution graph. So in the same way, or in the same understanding, we know that every normal distribution graph can be transformed back to a standardized normal distribution. And with the transformation formula, it's like this, it's just the standardization equation. So where x follows a standardized normal distribution, which has mean 0 and variance 1, and x follows a normal distribution with mean mu and variance sigma square, right? And how do we relate x together with z? It's just like z equals to x minus mu divided by sigma. Yes. And the reason why we are trying to do this kind of standardization is actually for convenience, for us to use the normal distribution formula. Because for normal distribution formula, what we have is that we have for each probability, we have a corresponding, like we know that z value. So which means that for each value, what we have for normal distribution is like, if I give a value here, I can see what's the error before that, or on the left-hand side of that. But that only works for the standard normal distribution. It does not work for every distribution. So in order to use that table, we need to convert every normal distribution back to the standardized normal distribution. Okay, so let's look at some examples about finding the probabilities. Then we can see the power of standardization. Okay, now we are seeing that for random variable x with normal distribution, so x follows n20, 16. So in this case, 20 is the mean and 16 is the variance. And find the probability of x smaller than or equal to 25. So we know that probability of x less than or equal to 5 is just equal to the probability. We use the standardization here. I think I will write a more detailed approach than this one, so you can see why this one works. Oops. Sorry. How do I open the notes? Okay. Okay.
Just check that it's still on the Google Hangout. If you go to window. Okay. No, it's still recording. Oh. Yes.
Yeah, okay.
Okay, thanks. Okay. So now we are looking at the finding the probabilities using the standardization. Okay. So now we are trying to look at what's the probability of x less than or equal to 25. And we use the standardization, we convert it to z. So we use x minus mu divided by sigma squared 5, because this also equal to 25. Like when we do some transformation for the left-hand side, we should do the same thing for the right-hand side. So 25 minus mu over sigma squared. And the probability of x minus 20 over 16 less than or equal to 25 minus 20 over 16. So we know that this one is just z because it's standardization. And this one is 5. Sorry, this one should not divide by sigma squared sigma. So this is 4. So this is 1.25. And now because it is a standardized normal distribution, so we can use the distribution table. And we can use the distribution table to see that this value 1.25 corresponds to 0.8944. Is it correct? Oh, no. It's correct, right? So it's just like 0.8944. And we should also take note of like this function. It always equals to probability of x smaller than or equal to x. So for example, for the next example, we are asked to calculate the probability of x greater or equal to 25. And in this case, we cannot just read off. Instead, we need to use 1 minus this value, right? So we get 0.10457. And what about next? Next, is a bit trickier than the previous part. So doing the same thing. Okay, next. Okay, so for next one, we have the probability of x smaller than or equal to 12. And by the same conversion, we have this 12 minus 20 over 4. And we have minus 2. However, we cannot find a number minus 2 on the table, right? So what number should we look at instead? We know that if this is a standardized normal distribution graph, this is minus 2. So we are looking for this area, right? So, but by symmetry, this area equals to this area.
Yeah.
And this area equals to 1 minus this area, right? And correct? So by symmetry, the red area is what we are going to find. And by symmetry, red area equals to the blue area. And the blue area equals to 1 minus the green area.
Yeah.
Because the sum of everything is 1, right? And this is 2. And we know that the green area is phi of 2, right? And so this one is just 1 minus phi of 2. So we find the value corresponding to 2, and then we use 1 to minus that. And the value corresponding to 2 is 0.9773. And we get our final results. So it means that if we have a z value of a negative value, or we have a negative value for z, it means that we cannot just read out the result from the table. So we need to convert that to the positive value. And I think it always helps if we can draw a graph so that we know that which bit we want. Do we need to use 1 to minus that bit? Yeah. And next part is also, okay, so next part is to find the probability of greater than or equal to 10 and less than or equal to 30. So it's a bit complicated, but it's not that difficult. What we need to do is just like we need to consider the both cases together and find the intersection. So we need to calculate what's the probability of x less than or equal to 30 and greater than or equal to 10. So probability of x greater than or equal to 30. So it's probability of z. What about 30? Is 30 minus 20 over 4. 10 over 30 over 4. Minus 20 over 4. And this one is minus 5. Oh, sorry. This is 20. Oops. This is minus 25. And this is also 25. And so we know that if this is minus 2.5, this is 2.5. We are trying to find the green area, correct? And what's the green area? It's just the red area minus the blue area, right? This blue area. It's just the red area minus the blue area. And what's the red area? The red area is just the corresponding value of 2.5, and the blue area is just 1 minus the corresponding value for the 2.5. And so this is just, we use this value to minus this value, then we get the whole results. Yes, so it's just like this value equals to 0.9938, and this value is 1 minus 0.993. So we calculate the difference between the two. Have a bracket here. Yeah, I think it always helps. Yeah, so the most important thing to take note is just like always draw a graph when you're not so sure about that. Okay, now we are actually trying to, so here it's like we are given a normal distribution. We are trying to find the probability, but we can also do it in an inverse way. So the next problem is actually a bit difficult, I feel, and it's also very important. It's like we are given the probability, and now we are going to try to estimate the normal distribution. What's the distribution for that? And we know that for a normal distribution, the two key parameters we need to find is the mu, which is the mean, and the normal distribution, which is sigma squared. Yeah, so now we are looking at the next problem. Sorry. Okay. So let's read the question first. It says, the length of body feathers of a particular species of bird are modeled by a normal distribution. A researcher measures the length of a random sample of 600 feathers and finds that 63 are less than 6 centimeters long and 155 are more than 12 centimeters long. So what do we know about this? So we know that it's a normal distribution. It's something like a normal distribution, but we don't, sorry. Okay. So we know that it's a normal distribution, but we do not know the mean and the standard deviation is. But we know that 63 are less than 6 centimeters long. So we know that if this is 6 or this is 12, we know that 12 should not be here. So with 6, and so we know that 6 here, and this, the area of this part is 63 over 6 600. And if this part is 12, then the area of this curve is 155 over 600. Yeah, so what we know is that the probability of x less than or equal to less than 6 equals to 63 over 600, and probability of x greater than 12 is 155 over 600. But this gives us nothing about the mean of the standard deviation. What we need to do is also to use the standardization. Like we can just do one example here, and we can read the notes about the second example, or you can try the second example by yourself. So for the first one, after standardization, we can get z less than 6 minus mu over sigma equals to 63 over 600. So we know that 6 minus mu over sigma equals just to the phi inverse of 63 over 600. So now we are trying to look at that probability value and see which value it corresponds to, right? And so we get an equation about 6 minus mu over sigma equals to what? And this is our first equation. So in this case, we find that 6 minus mu over sigma is minus 1.253. And one thing to take note that is it's actually 63 over 600 is too small, that we do not have this number on the table, right? If I'm not wrong, all the numbers on the distribution are quite big.
Yeah.
So it's like, for example, this is standard normal distribution, and so here is 63 over 600. So this value, we want to find this error, but this value is too small that we cannot find this error directly. So what we need to do is to find a symmetric part. So what about it's correspond? So this is the error, right? So what you need to do is to find the error of this one. And we know that the error of this one is just 1 minus the 63 over 600. And then we try to inverse that. We find the phi inverse of this big error. Then we know this value. And this value, by symmetry, is just the opposite of the value over here. So in this case, 63 over 600 is 0.105, which is too small to be found on the normal distribution table. So we find so we know that we use 1 to minus this part to get 0.895. And we found the value for this is 1.253. So it means that the value for the 0.105 should be minus 1.253. So again, it's using the symmetric property of the normal distribution curve or graph. And similarly, for the 12th part, we can do the same thing and have an equation like this. And then our next job is just to solve these two equations together and to get sigma and mu. Do we have any questions for this? Okay, and then we are looking at next part. In a random sample of 1,000 body feathers from birds of this species, how many would the researcher expect to find with less more than 1 standard deviation from the mean? So this part is we will use the result from the previous part. So now in this case, we have a normal distribution. And then we know that we know the mean and standard deviation for that. However, we do not actually need to use that. What we need to use is that it's just we need to know the probability of that more than one standard deviation from the mean. So what we need to do is still we draw a graph for the standard normal distribution. And because we know that for the standard deviation, it's for the standard normal distribution, its standard deviation is 1. So one standard deviation away, it just means that probability for Z is greater than 1, more than one standard deviation away from the mean, and plus the probability of Z less than or equal to -1. So we're just trying to find the area of this graph, right? And what's this value? We know that it's just like 2 times 1 minus psi 1. Right, because phi of 1 is equals to this blue area, and each small bit of the right areas is just 1 minus phi of 1. And altogether, consider both the left tails and right tails, we get 2 times 1 minus phi of 1. Yeah, so in this case, we know that phi of 1 is 0.847, times 2, so the probability is 0.3174. And because now we have 1,000 body feathers, so what's the expected value? It just use 1,000 to times the probability to get 301 and 17 birds. Are you okay with that? Okay. So now we are coming to the final part and the last part of the binomial distribution, and which is the approximation. Because do we remember that just now we are talking about the binomial distribution? It is for the discrete case. So this approximation part is actually to connect the discrete cases together with the continuous case. Why can we do that? Because we remember for the continuous case, the normal distribution graph looks something like this. And about the discrete case, we know that the discrete case, it also has some expectation value, right? Which just now I mentioned it kind of have the largest probability. So it's like we also have some probability going something like this. And if we have enough points, or when n is large, and this is actually approximated, it is approximately like a continuous graph of the normal distribution graph, right? So this is the reason behind why we can do the approximation of a binomial distribution with a normal distribution. But why do we need to do that? Because sometimes when n is very large, remember our formula for the binomial distribution, we have to do something like choose 10 out of n or choose 5 out of n. When n is very large, then the calculation is very kind of tedious. So when n is large, we do not want to do the calculation for the binomial distribution. Instead, we approximate the binomial distribution to a normal distribution. Then it is easier for us to calculate and to estimate the probability. Yeah, so these are the two, this is the reason and the rationale behind this approximation. Okay, so what's the condition for us to do the approximation? So for a binomial to be converted to normal, it must have NP greater than 5 and NQ greater than 5. Yeah, so it kind of means that N should be at least larger than 10, right? Because we know that at least one of P and Q should be smaller or equal to 0.5. So in order for this to hold true, N must at least be greater than 10. But however, in some case, for example, if P is 0.1, Q is 0.9, in order for these two to both hold true, N has to be greater than or equal to 50. So it really depends on P and Q. And if the conditions are met, then the binomial distribution is equivalent or approximately equivalent to the normal distribution. So how do we change the parameter? We know that N represents the number of trials, P represents the probability of success. And for the parameters in the normal distribution, the first one is the mean, so which is equals to NP, and the second one equals to the variance, which equals to the NPQ. for the binomial case. Yes. So I think for this part, we just need to take note of what's the condition for this approximation and how do we convert the respective parameters for each distribution. And another thing to take note when we are doing the approximation question is about this continuity correction factor thing. Because we know that for binomial distribution, each case is discrete. So we do not have a value of 5.5 or 6.5. What we have is just like 5 and 6. So, but for the normal distribution, it actually has a range. It is a continuous. It does not make sense if we use probability of, for example, we are trying to calculate probability of x equal to 6 for binomial distribution. It makes no sense to calculate the probability of x equal to 6 for normal distribution because this is 0 for continuous distribution. So in order to do this part, we have to do something called the correction factor. And this is something we need to take note of. So x equals to 6 corresponds to the, so basically, let me draw a graph to illustrate this. So basically, okay, 6. So if it's 6 for the normal distribution equals to 6, we are considering this part. And if it's greater than 6, because for binomial distribution, if it's greater than 6, it must be at least 7, right? So in order to take note of the range, we have to do it's larger than or equal to the 6.5. And similarly, if it's greater than or equal to 6, it's greater, for normal distribution, it's greater than or equal to 5.5. So it's like for each value, we just use the left half and right half of it. Yeah, this is something we need to take note. It's not that hard. Now we are looking at the final questions on these notes. Oops. On a certain road, 20% of the vehicles are trucks, 16% are buses, and remainders are cars. A random sample of 125 vehicles is taken. Using suitable approximation, find the probability that more than 73 are cars. Okay, so what are the steps of us to approximation question? First of all, we need to find its binomial. First, step 1. Find the binomial distribution. Right. So what's the parameter? So x follows. What's n here? 1, 2, 5, right? And p, that's 1 minus 0.2 and minus 0.16. So it's 0.64. It's a probability of for a vehicle to be a car. And step 2, we need to check whether we can use the approximation. So it's check the approximation criteria. I know sometimes it may sound silly for you to check the criteria because since the question asks you to use a suitable approximation, it definitely means that you can use the approximation. But just in order to show that you understand the condition or the necessary conditions for this approximation to work, you need to check that. So you need to show your understanding that NP equals to what? NQ equals to what? So in this case, NP equals to 80 and NQ equals to 45. So both are greater than 5. So it means that we can use the approximation. And the next step, so the step 3 is just to convert it into a normal distribution. So what's that? Sorry, I missed a B here. So NP equals to 40, so the mean is 40. And we need to use 125 times 0.64 times 0.36 to get the variance, which is 28.8. Now we have a normal distribution. Then what we are left to do is to use a normal distribution to find the probability of that having more than 33 cars. And in order to take note of the continuity part, we have to put 73.5. Okay. So, and then we do something like the standardization, say 7.35 minus 80, sorry, and divided by 28.8. And then using the method we are talking about here and our normal distribution table, we can see that what's the probability. Yes, so for the approximation part, always first write down the distribution in terms of its binomial form by finding n and p. Then we check whether it fulfills or satisfies the approximation criteria. We need to calculate np and nq to verify that both of them are more than 5. And the next part is to convert the problem into the normal distribution. And as we convert, there are a few things we need to take note of. First, we need to calculate the mean and the variance. And second, we need to do the continuation. We should do the continuation, like to convert the discrete number to the continuous number by adding or subtracting 0.5 depending on which you have. And later we are just using the method above. We are using the standardization and the normal distribution table to find the value of the probability. Yes, and so I think that's all for normal distribution, and it's also everything for the statistics 1 course. Yeah, so now I think before we move on to the paper for today, because I think I'm only going through like 2 questions on the paper which cover today's courses, I would like to do a quick summary of what we have done or what we have learned today, and also some things to take note of. So it's summary for today. So what we have done today is just probability distribution. So for the probability distribution, first we know that it basically tells us about the random variables. It's the random variables and also the probability for the random variables to take on different values. And then we divide that into 2 different cases. One is a discrete cases and the other one is a continuous cases. And for discrete cases, we have binomial distribution. And for continuous case, we have normal distribution. And for binomial distributions, we know that it follows something like B and P, where N is the number of trials, P is the probability of success. And we also learned that there are 3 conditions we need to take note in order to use the binomial distribution. One is that it only has 2 possible outcomes and they're mutually exclusive. The second one is that each individual case is independent of each other. And what's the third one? Sorry. Okay, so the third one is fixed number of trials. Yeah, so fixed number of trials. And next, we learn about how to calculate that. So it's C choose. So probability for x equals to r, it's just C choose r, p to the power of r, and 1 minus p to the power of n minus r. And also we talk about the expectation value, which is np, and I tell you how to prove that, but that's not required to know for the exam. And what the variance is npq. So this is everything we learn for binomial distribution. What about normal distribution? We learn that it follows something like n mu sigma squared. It's mean and variance. And we also talk about the the standardization, because it's very important for us to use the normal distribution table. And in order to use the table, we have to convert that to the z. So z is equals to n minus mu divided by sigma. And after that, we talk about the approximation. approximation parts. So approximation part is actually something related to both the discrete and continuous function. It's a link between the two. And here we talk about the steps of doing an approximation. First of all, write down into the binomial distribution form. And the next step is to check the criteria, which is that NP greater than 5 and NQ greater than 5. And the last part is to convert that to a normal distribution and calculate. And something to take note of is the correction of the continuity. Yes, and I think this is everything we have learned for today. And I hope that you have a clearer idea of what's going on for the probability distribution. And for the last 20 minutes or 15 minutes, I'm going to look at some of the past exam papers. Okay, probably I think I can give you like 2 minutes to read the question 1 and think of how to do that first, then I will go through that. Like we are only going to do the first and last question. So we are looking at the first questions. First is Statistics 2014 summary. Okay, shall we do that together? And so, first of all, we identify this is a binomial distribution kind of questions. And so, because as we talk about examples, I was basically talking about the ideas and how to solve each questions. And now I want to talk about a little bit about like how we can do the questions like during the exam, like how we should present our answers. So first of all, we should define our variables. I know that sometimes the variables is all very obvious, like which is the random variable. Like we usually just put an x and write down x for some distribution. But I think it is a good habit to always define the variable first so that you know what we are talking about. And in this case, they say that find the probability that fewer than 4 houses have solar heating. So we know that the very random variable is just the number of houses with solar heating, right? So it's x. So first, let x represent the number of houses with solar heating. And next step, we want to find which distribution x follows. It follows binomial distribution, but what are the things we need to fill in here? One is n, and the other one is p. So the n is what? The total number of houses is 19. And what about p? Because it says that 12% of houses have solar heating. So the probability for a house to have solar heating is just 0.12. Yes. And the next step is to write down the problem and to calculate what's that. So in this case, fewer than 4 houses, so probability of x smaller than 4. But we know that we only have the formula for the probability of, what we know about binomial distribution, we only have the probability of x equals to x equals to n choose x, p to the power of x, q to the power of n minus x. But we do not have a probability of less than or equal to or for the probability of an inequality. So we need to divide the case into all the individual parts, because we know that x can only take integer values. So probability of x less than 4 is just equals to the sum of these 4 different cases. And then we plug them into the formula of the binomial distribution. Then we can do the final calculation. So I will not go through the detail for that. You just substitute 0, 1, 2, 3 in this formula. And now we are looking at the last question. And it's clearly say that it's a normal distribution problem. It's a normal distribution problem. Yes, I will again give you 2 minutes to look at the questions. Okay. So I think it's a good habit that sometimes as we read the questions, especially the question is a bit long, we try to convert everything in English into something in math so that we learn how to deal with that. And first thing first, even though this question does not ask us to calculate any probability, like especially for the first part, but I think it's still a good habit to identify what's the random variable. And in this case, it says that the time he spends on his homework each day has a normal distribution with mean blah, blah, blah. So the random variable is just the number of hours he spends on homework each day. And x follows a normal distribution. So we write down what distribution x follows. X follows n, and mu sigma square, whereby mu equals to 1.9. And sigma is unknown, is what we are going to calculate. And what about next? On 80% of these days, he spends more than 1.35 hours on his homework, which means that the probability of x is greater than 1.35, just equals to 80%. So it's 0.8. And now we are going to find the sigma. And what we are going to do here is standardization, because we can only find the relation between the x and probability when it is converted to the standardization form, or standardized form, sorry. So it becomes probability of z greater than 1.35 minus 1.9 over sigma is equal to 0.8. Sorry. So we know that our next step, it means what? It means probability of z smaller than or equal to 1.35 minus 1.9 over sigma is 0.2, right? So now we know that this value, it corresponds somewhere here, and the area of this part is 0.2, right? But we cannot just read 0.2 from the table, so we try to find its image, like we try to find what this value is. And we know that the area of this blue area now the area of this blue region is 0.8, right? Correct? So by finding the value corresponds, by finding the inverse phi of 0.8, we get this value. And we put a minus sign, it's just this value. So now we are looking at what's this inverse 0.8. You can also find by yourself. So the Z value is 0.842. So we can find that the inverse of 0.8 is 0.842. So we know that 1.35 minus 1.9 divided by sigma equals minus 0.842. And then we can calculate sigma, which is 0.653. I will equip the first part. Okay, now we are looking at the second part. Find the probability that on a randomly chosen day in term time, Rafa spends less than 2 hours on his homework. So it's just the probability of x less than 2, right? And what's that? It's probability of z less than 2 minus 1.9 divided by sigma is what we calculate just now. Sigma is 0.653. So divided by 0.653. Yes. And I think you can calculate this value by yourself and look for the answers on the normal distribution table. And the third part. A random sample of 200 days in term time is taken. Use an approximation to find the probability that the number of days on which he spends more than 1.35 hours on his homework is between blah, blah, and blah, blah. So we know that in this case, the random distribution, the random variable becomes the number of days, right? And it is actually a binomial distribution, whereby y follows a binomial distribution of what? N equals to 200, because this is the total number of days. What about the probability? We see that the number of success means that if he spends more than 1.35 hours on his homework, then it means a success. So we need to know what's the probability for him to spend more than 1.35 hours. And this is actually very easy because we know that 1.35 is the mean of the distribution, so it's just 0.5. So it just means that what's the right half, the area of the right half region, so it's 0.5. This is the probability of he spends more than 1.35 hours on his homework. And now, because they say that using an approximation, so we want to approximate that to a normal distribution of what? And before we can approximate that, we need to check. Okay, I think I can use a new box to do the third. Okay, the third. Oops. Okay, so the third part is an approximation problem. And we define the first part, we define y is the number of days on which he spent more than 1.35 hours on his homework. And y follows a binomial distribution of 200 and 0.5. And we check that 200 times 0.5 is 100. And both NP and NQ equals to 100. It's greater than 5. So it's okay. We can approximate that to normal distribution. So y follows the normal distribution of what? Of 100, which is the mean, and 50, which is the variance. We use n times p times q. And later, we just use the normal distribution to find y. It says it's between 163 and 173, but we know that we need to take note of the continuity. So it says inclusive. So we have to 173.5, 162.5. So whether it's inclusive or exclusive, very important. Take note of that. And we just find these parts using the normal distribution. So this is the 3 steps for us to do the last part. Yes, and if you go back, you can actually look at the answer marking scheme. Yeah, so, oh, 0.5. I think actually the variance is NPQ, right? Let me just double check. Yes, yeah, the variance is NPQ. And in this case, both P and Q. Oh, yeah, I think just now I made a mistake because just now I thought like here is a 1.35. So I thought at 1.35 is the mean, but actually it's not the mean. It is the mean is 1.9 hours. So for our binomial case, it's actually follows a binomial of 200 and 0.8 instead of 0.5. Yeah, so 0.8. So P is 0.5 and Q is 0.2. Sorry for that. And so the binomial distribution is the 200, 0.8. And we check both NP and NQ are still greater than 5. And normal distribution is 160 times 160 and 32. So 160 is the mean, which is n times p, and 32 is NPQ, which is 200 times 0.8 times 0.2. Yeah, and I think the rest of the steps should be the same. Okay, so I think that's all for today.
Yeah.
Okay, thank you.
Thank you.
So now I can finally stop. I can stop. Yes.
You go on.